we shall begin. Okay, let me do a brief just review and recap of last week. Let's make sure we understand stuff from chapter 4. Okay, so you guys just turned in, or you completed your homework and you turned in the papers that said you did chapter 4's homework. Let's just make sure we can do chapter 4's homework. Okay. Okay, so let's say, all right, listen up, you guys. So let's say this is a model to linear regression model to predict the price of a car based on its age. Okay. Actually, let me just change this to 22. Okay. 22,000 minus 1,800 age. All right, age in years. Let's say R equals 0.8. Okay, so I'm going to say predict price of a car that is 5 years old.
Coefficient supposed to be negative, not
Good catch. Okay, go ahead and take a few minutes to answer those questions. we doing?
I don't remember the reciprocal. What that means.
Okay. Well, you'll need to know. It's good. Now you know that you don't know that.
I don't remember.
Okay. So these are all things you need to know. Hey, what's our answer here?
13,000.
13,000, right? I did change that first number to 22,000, so if you had the old number there, you might have changed your answer. I was just walking around, I saw some people with negative numbers, or just some crazy numbers, okay? Now, all of these things, whenever you do math, and especially statistics, there should be a moment right before you write down an answer where you say, does this even make sense? Okay? Does this even make sense? So, what is the purpose of this model? We are trying to predict what? The price of what? Of a car based on its age. Okay, so we're saying if you got a brand new car, it's worth $22,000, and as the car gets older, it's worth less. Okay, that sounds reasonable, right? Okay, so we try to predict price of a car based on the age of the car. Okay, so we got $13,000. Is anyone having trouble getting this? Okay, all we did was we took this number 5 and we plugged it into age. Put that in our calculator, spits out 13,000. Okay, if the actual price of this said car, of this car that we're talking about, is $15,000, what is the residual?
2,000.
2,000. Positive 2,000 or negative 2,000? Positive 2,000. Okay, so we just do 15,000 minus 13,000, and we get $2,000. Positive 2,000. Okay.
What does the word mean?
The residual is the difference between what we predicted, the actual price, and what we predicted, okay? So the residual is
Thank you.
so if you are selling the car, if you're the one selling the car, would you prefer to have a positive residual or negative residual? Positive, right? Because then that means your car is worth more than what the model predicts, and we would prefer that if you're the one selling it. Okay, simple question, which variable is the dependent variable? The price of the car, okay? So this is the dependent variable is the y, and that would be the price. We are predicting price, okay? Another way of saying dependent variable is the variable that we are trying to predict. Alright, and on the flip side, what do we have? The independent variable would be age, and that is the variable not we try to predict, but we use to predict. Okay, we use age to make the prediction. Alright, what is the slope and its interpretation? Okay, our slope is negative 1,800, and it's negative 1,800 what? Dollars per year, okay? And what does that mean? That means the interpretation is
By every additional dollar.
For a year
additional
older,
age.
the price goes
1 year
down.
old.
Okay, so I heard some of you guys say it, and then I heard other people say the wrong thing. So, it's for every additional year in the age, okay? When we say year, we automatically, age is understood. Okay, for every additional year, we predict and it's important that we use the word predict, okay? Because this doesn't mean this. It doesn't mean that it always happens. It's just we predict that this happens. We predict that the price goes down $1,800. Is this one mine or is this? That one's yours. Okay. No. Just, all right. So far, so good? Okay. There's one thing I didn't mention or talk about last class, and that is R squared. Okay. So if you take that value, R is negative 0.78. This is our, what do we call this? Correlation. This is correlation. And if we square this, then we get big R squared, so that's 0.78 times 0.78, or negative 0.78 squared. What does that turn into? 0.6084. Okay, this is my R squared value. This, you can think of this as a percentage, okay? So about 61%, 60, 61%, okay? It is the percentage of the variation in Y that is explained by the model. That's what R squared. Okay. So what does that mean? It's the percentage of the variation in Y that's explained by the model. Okay. What is Y in our model? The price. Okay. So if you just looked at a bunch of different cars, they have different prices. Okay. That's the variation in price. This R squared says, you know, cars have different values. And we can explain about 60% of that variation according to this model. Okay? There's some of it that we can't explain. It might be tied up in, you know, other, you know, the condition of the car, et cetera, et cetera, et cetera. But we can explain about 60% of the variation based just on the age of the car. Okay. So that's what R squared is. So it's the percentage of the variation in Y that's explained by the model. Is that okay?
It explains the variation in price.
In price, or you know, whatever your linear regression model, it's got a Y and an X, right? So whatever your Y is, it's how much of that variation can you explain? So it's just okay, so these are all things you've got to know regarding linear regression. I mean, at least this, right? There's probably, you know, some more topics that you guys have to know, but at least this will give you an idea of some of the things you need to know. Okay, and if you find yourself, you know, whenever I do these problems on the board and ask you guys to do it, and if you find yourself just sitting there, having no idea what to do, okay, please seek some help and ask questions or do something, okay, or at least, you know, try, because otherwise it just turns into a waste of your time, okay, and the purpose is so you guys can work on it, figure out what you know, what you don't know, or gain confidence in getting certain things right. Alright, today we move on to chapter 5. And chapter 5 is, it's like we're taking a small detour into the land of probability. Yes, question?
We were wondering about that exercise, how you got the slope minus.
Sorry?
We were wondering how you got the slope of minus 18.
From the model, or how I made up that model? So the model said price hat, so predicted price is equal to 22,000 minus 1,800 H.
So the slope is just the 18 and minus 1800?
Yeah, this is the slope, right? It's A plus B X, okay? And so the number that comes here is the slope. All right, we're going to move on into probability. Traditionally, most students hate this chapter, okay? It's just, you know, some students like it, but traditionally, this is one of the least favorite chapters, okay? But it's important that we go into it, okay? Because a lot of what we do in the future is based off of concepts from probability, okay? Now, because this is an introductory course, sometimes the chapters feel unrelated, okay? Like, when we move on to next week, it's based off of this previous week of chapter 5, but you really have to get really deep into chapter 5 stuff, okay? To really fully understand what we're doing next week, okay? But that said, we're going to just take an introductory look at probability, okay? And then we will move on into stuff from chapter 6, which is built off of this, but because, you know, we're kind of going at a shallow, it's an introductory course, so we only do a shallow bit. It feels a little bit unrelated, but I promise you that they are connected, right? It's like learning chemistry and combustion to understand how an engine works, okay? They are related, but, you know, at the surface maybe you don't quite see it. But that's okay, all right? All right, so with probability, we are trying to model the chance that an event will occur, okay? That's what probability is all about. There's some event, and it may or may not happen, and we're trying to assign a number to that event, okay? That tells us how likely or unlikely it is to happen, okay? That's the overall concept of probability, okay? So there's some event, okay, and we want to assign a number number is known as the probability of the event.
One of them. So the measures.
Okay, I'm gonna roll this up. Okay. So we might have some event, okay, and we label it A. Alright, some event A. So we say the probability of A maybe equals 0.7, okay? This number tells us how likely this event A will happen. Okay? Any event, all probabilities are decimals. Okay? So you have to be comfortable with dealing with decimals, otherwise we are in big trouble. Okay? And we know the rules of multiplying decimals, right? Okay? And we know that moving that decimal place forward and backward has serious implications. What multiplying by 100 does, what dividing by 100 does, all of these things. You got to be comfortable with decimals, otherwise this chapter is going to be a disaster. Okay. If you're struggling with this chapter, it's probably because you have forgotten your rules on decimals. So if you need to go back and learn decimals, take this week and learn decimals. I don't want to say any more than that because this is statistics and it's assumed you guys all know decimals, but year after year, I always see the same decimal related mistakes. Okay. So all probabilities are between 0 and 1 inclusive. Okay, so it can be as small as 0, including down to 0, and as large as 1. So if you ever get a probability bigger than 1 or smaller than 0, you did something wrong. Okay? So if you ever get a probability that's implied by this sentence, but I'm going to write it because I always get students who write other things. You ever get a probability bigger than 1 or smaller than 0, you did something wrong. Say that rule, we just say probability of A is these two things say the exact same thing. Okay. If probability A equals 1, then A always happens. A equals 0, then event A never happens. and everything in between. So, we said probability of A equals 0.7. What does that mean?
Pretty much 70% of the time.
70% of the time? Okay, what does it mean to happen 70% of the time? Hmm?
Happens most of the time.
Happens most of the time? Okay, what is...
It's
Alright.
likely to happen.
Okay. So here's an example. Let's say I have a bowl, okay, and I've got some candies in here. All right, I've got 10 pieces of candy in the bowl. 7 of the candies are, let's say, red. Okay? 10 candies total. If I shake up the bowl, close my eyes, reach in there and grab one of the candies, the probability that I draw a red candy is 0.7. Okay. But again, so I've given this event a number, and it makes sense. I've got 10 candies in the bowl. If I just close my eyes, reach in there and grab one of them, I've got a 0.7 probability that that candy is red. Okay. Is that okay with everyone?
Yeah.
Okay. But what does it mean that the probability is 0.7? Does that mean if I reach in there and grab one, is it going to be red for sure?
No.
No. What if I reach in there, you know, is it not going to be red? It doesn't, we don't know. The idea of this 0.7 comes from the long run relative frequency, okay? And the idea there is, let's say I reach in there and I pull out a candy and I look at it, okay? I open my hand, it's red, okay? I'm gonna go over here and I'm going to say, trial number 1, candy was red, okay? And I put the candy back, I mix it up, I close my eyes again. I reach in there, I pull out another candy, I open up my hand, and what is it? It's red, okay? So I go up and I write trial number 2, candy was red. I put the candy back, I shake it up, I reach in there, I pull out another candy, open my hand. It's not red, okay? So I go trial number 3, not red. And I do this over and over and over again. I spend the rest of my life doing this. I do this. You know, let's say I get to 50,000 times, okay? So I'm like 85 years old. All right. It's red, okay? And I go, trial 50,000. Candy is red, okay? And then I submit this, and I say, this is my life's work. Have I uncovered the mysteries of probability? Okay? So can we imagine a silly scenario like that? Okay? So just imagine, you know, I'm keeping trial 1, candy is red. Trial 2, candy is red. Trial 3, not do this thousands and thousands of times, maybe millions of times, who knows? Well, the relative frequency let's look at the relative frequency. So the relative frequency after one trial is what? I had one trial and it was red that one time. So it's 1 out of 1. My relative frequency is 1. Okay? What about after 3 trials?
1, 2.
Okay. My relative frequency is that I've done 3 trials and 2 out of 3 were red. So I have 0.667. Okay. Now I know some of you guys get this, and some of you guys are just copying down stuff I'm writing on the board. But I want to make sure you understand why I'm writing 2 out of 3. And if this is unclear, please take a moment and raise your hand. Okay.
Do you need to label it red or something like that? Or you just?
Yeah, so, okay, so I'll say relative frequency of drawing a red candy. I'll write that. How's that? Okay, so after 5 trials, what is my relative frequency? 3 out of 5.6, okay? The idea is, if I do this, so after 50,000 trials, okay, what am I going to have? I'm going to have something very close to 0.7. We have a question. I'm sorry? Yeah, so after 50,000, I might not have exactly 0.7. I might have something like 34,983, okay, out of 50,000. Okay, and what is this? This is going to be 0.69966, okay, I think. So it's not exactly 0.7. Is that right? Somebody verify?
Where did you
Yeah,
go?
it is.
But it's not exactly 0.7, but it's pretty darn close, right? And that's where we're getting this idea of relative frequency.
Where did you get the 34? Or did you
I just made that up. I just said I'm just pretending. I'm dreaming into the future, and I'm picturing 50,000 of these trials, and I'm 80 years old, and I'm drawn out.
This is total, right? Total.
Yeah. So just imagine we keep doing this, okay? After 1, after 3, after 5, after 50,000 trials, I've drawn 34,983 red candies out of 50,000 trials total. This turns out to be this per decimal, okay, which is very close to 0.7. Listen up. Okay, so after many trials, our relative frequency approaches the true probability. These relative frequencies, there's another word for it. We call these empirical probabilities. Empirical meaning based on evidence or based on observation. So these are what we've done from observation. Okay.
True.
probabilities. Alright. So the relative frequencies we observe are called empirical probabilities, and what we see is that after many trials, the empirical or relative frequencies approach the true probability. Okay? And that's part of this thing that we call the law of large numbers. Which states that as we perform more random trials, we expect the empirical probability to be closer to the theoretic probability. So this notion of saying that the true probability is 0.7 is the idea that if we did this many times, our relative frequency should be very close to 0.7. Okay, that's basically what we're saying. Okay. But obviously, we might not be interested in doing the same thing over millions of times or thousands of times. And we're just going to do something once, okay? So what happens that one time, might surprise us, right? If I say name a card and you say the Queen of Spades, and I reach into a deck and I pull a card out and it's the Queen of Spades, you'd be surprised, okay? But the truth is, it's about 1 in every 52 times that might happen. Okay? And so, on any one given occasion, something unexpected might happen. But that happens. If I do that same trick over and over and over again, we would not expect me to pull out the same card every single time. Okay, so we're going to learn. So this week's chapter is going to focus a lot on the rules of calculating theoretic probabilities. Okay. The chapter mentions a little bit about simulation and empirical probabilities, okay? And basically that's basically just doing the random trial over and over and keeping track of your relative frequency. It's reaching into the bowl, pulling out candies, and keeping the log. But to speed things up, you use a computer to kind of simulate the bowl of candy, and the computer keeps track of this, and it can do thousands of repetitions very quickly. But that's finding things through empirical probabilities. And people do that actually quite a bit these days, because the rules for calculating theoretic probabilities can get really complicated and difficult to do. And it's actually easier to go to the bowl of candy and reach in there and draw out and see what happens. Okay? So a lot of times people use the computer to do the simulations because it's actually easier to do kind of that brute force method than to try to calculate theoretic probabilities yourself. But in our class, we're just gonna do the kind of the surface and learn just the basic rules of theoretic probabilities, which we should all be able to do. But even those basic rules, students generally hate them. So, but we have to do what we have to do. So, all right. So let's we will start. Okay. So. Just a few things. So if we have event A, the event A has probability A. Okay, so has probability that's going to happen, probability A. So there's something called the complement of A, which means event A did not happen. This is called complement. Complement with an E, not compliment. Something nice you say to a friend or an enemy to gain their trust. The complement of A, you might call not A, or sometimes we write a C for a complement, and this has probability 1 minus the probability of A. Okay, so very simply, if the probability of drawing a red candy is equal to 0.7, it's very easy. What is the probability I do not draw a red candy? Very good. This is equal to 0.3. And we got that by doing 1 minus 0.7. Simple, basic rule, but it comes up a lot. All right, we have a situation, a special situation called simple outcomes. Special situations with simple outcomes. Simple outcomes mean the outcomes are all equally likely. So we have, let's say, so the probability of some event A is equal to the number of outcomes in A divided by total number of total outcomes. So, one example was my bowl of candy. And I said, I said 7 of them are red, okay? So probability of red candy was that 7 are red divided by 10 candies total. What about a die? Rolling a die. So die has 6 sides. Okay. What is the probability of rolling an even number? Yeah. Okay, so there's three numbers that are even, 2, 4, and 6, out of 6 faces total. So we have 3 out of 6, 0.5. Okay, I'm gonna just push that up to the top. Is that okay?
Yeah.
All right. Let's say I've got a giant room with a lot of people. Okay, lots of people. All right. There's only. All right. So just imagine a giant room here, okay? And I'm keeping track of a few categorical variables. Let's say I want to keep track of sex, and I want to keep track of, let's say, right hand or left hand. Okay, how can I summarize all of this information?
In a table?
Yeah, what kind of table? What do we call this thing?
Category?
A two-way table. I've got 2 categorical variables. I can keep track of this with a two-way table. Right? Good. So let's say I have males, females, right-handed, left-handed. And let's say I've got a total of 900, and I've got 430 males and 470 females, and let's say 50 and 45, so that gives me 95 and 5. Okay, so rather than pieces of candy, now I've got 900 people in this room, alright? So if I have a giant claw machine, okay, or that, let's say I just pick people out of this room at random. Okay. What is the probability that I get someone who is male? So I pick someone at random from the room at random. What is the probability that this person is male? Yeah, 430 out of 900. Okay, so it's the same. It's almost just like drawing a candy out of the jar. Okay, except now it's a room with 900 people, but still, we're just picking someone at random. Every person has an equal chance of being selected. Okay? So this is still a simple outcome. Number of outcomes in A divided by total number of outcomes possible. Okay? So there's 430 people that are classified as male out of 900 people total. Okay? What is the probability that I get someone who is a left-handed female?
59.
Yeah. 50 divided by 900, okay? Because here, I'm still just picking someone at random from the room, 900 people total, and how many people qualify as left-handed females? 50 of them, okay? So it's still number of outcomes in A divided by total number of outcomes. 50 out of 900, is that okay? Okay, great. And but then we can make things more complicated, okay? All right. Rather than picking from the entire room of 900, I can then say, you know what? I'm only going to pick from the males, or I'm only going to pick from the females. Okay, so I'm going to say, you know what? If I pick you, and so let's say I'm only going to pick from the males, then I say if I pick you and you happen to be female, don't allow yourself to be picked. Okay, so this is changing it up, and we're going to use this term called given. Okay, and it's a funny word that we use, given, but it just means given. So that just means we're limiting ourselves just to one specific condition, okay, or an event per se. Okay, so I could say, what is the probability of picking a right-handed person, right-handed, okay, and I'm going to write given, this vertical bar stands for given, that this person is male. Okay, so this means I'm limiting myself only to the males. And what's the probability that this person is right-handed? So this is 385 people out of 430. What? Okay. So this means, so I'm just using the information from the table. It says, so I'm limiting myself, okay, so male is quote given, right? So that means we are limiting ourselves just to the males. Here is you're asking.
So Professor, for like process and stuff, will you tell us it's given, or will you write the little divider?
Yeah.
How will you know?
Yeah, so you have to be comfortable reading it with the divider or with the word given. Okay, you have to be able to see that this and this are saying the same thing. All right, is that okay? 385 out of 430. Yes, question. Okay, because, so there's a difference. So over here I said, what's the probability, I'm going to just pick someone from the room at random. What's the probability that this person is a left-handed female? I said, well, there's 50 left-handed females out of 900 people total in the room. Over here, I've changed it up. I said, here I'm asking, what's the probability that I'm getting someone right-handed given that this person is male? Okay? So I'm limiting myself not to all 900 people in the room, but just to the males. Okay? And there's 430 males. Okay, so it's easy to see this 385 out of 430 from this table here, okay? I'm gonna put up kind of this, like a generalized probability rule or something, put it in symbolic form, and you guys are gonna hate it, but that's just, you know, I start off with the examples so we can see it, and then I generalize to these things that everybody hates, but that's just how we have to do it, okay? So the generalized form is, and I just want to make sure I'm matching the same notation as the book. Do they say B given A, or yeah, A given B? Okay. The probability of A given B, okay, is equal to the probability of A and B divided by the probability of B. It's just the rule that you're going to have to write down and feel okay with, okay? That's all we've done here, okay? Except, you know, it doesn't look like this because we have a table and we're using real numbers here.
What is this called?
I don't know. The probability of A given B. It's the equation for finding this probability. Okay? I don't know. Conditional probability.
This is for the very huge, complicated.
No. This is probability of A given B. Okay? This is probability of right-handed given male. Okay? And we said that's 385 out of 430. And most of you, I think, nobody raised their hand, so I'm assuming most of you feel okay with 385 out of 430. Okay? If you don't feel okay, please raise your hand so we can make sure we're okay. Alright? So if you're okay with that, then you should be okay with this. Okay? It's just this is symbolic, and people generally like numbers over symbols. I can't blame you. Alright? So let me just show you. Okay, so see this probability of A given B equals probability of A and B divided by the probability of B. So, using our example, we're going to say the probability of right-handed given male. Okay. So all I've done is I've replaced the letter A with right-handed, and I've replaced B with male. And I'm just going to do that for the other side. So this is going to be probability of right-handed and male divided by the probability of male. So far, so good, right? All I've done is, it's like Word. Control F. Wherever you see A, put in right-handed. Autocomplete. New rule. Replace A with right-handed, B with male. Okay, so we've got this. All right. What is, okay, so just going back to here, if we pick someone from the room at random, we didn't do this one, but what's the probability that this person is a right-handed male? Right-handed and male. If I pick someone at random from the room. 385 divided by 900. Okay, that's this top probability. The top probability is 385 out of 900. Okay, and what is the bottom probability? 430 out of 900. Okay. Are these okay? You have a question?
When I see like right-handed and male, I kind of thought like the male meant like all the male, but it's like everybody in the class.
This is it's just right-handed and male. So when you see probability of right-handed and male, that just means if I pick someone at random from the entire room, what's the probability that this person is right-handed and male? Okay, that you guys answered this question the same way. Left-handed and female. Left-handed female, you said 50 out of 900. That's all we're doing here. Right-handed male, 385 out of 900. Yes.
Okay, I understand, but my only question is, how come is right-handed given male, which would be 385 over 430?
Okay, we haven't finished.
Oh.
Okay. All right. I just want to make sure that we're okay with getting 385 out of 900 here and 430 out of 900 here. Okay. We see right-handed and male, and we get this, and we see probability male, and we get this. Okay. So all I'm going to do is I'm just going to put 385 out of 900 on the top, and on the bottom I'm going to put 430 out of 900. Is this okay? All right. Do you guys remember your rules of fractions, and what do you do with something like this? Yeah, you take this one, all right? So this one becomes 385 out of 900 times, and then you flip this bottom one, you get 900 over 430, right? Is that good? And then you do this, and you get 385 out of 430. Which is exactly what we did up there. Okay? That's all I'm trying to do. I just want to show that we can use this thing to get what we did up there, alright? You're going to say, well, this was so much easier. Why would I ever want to do this? Okay? Well, sometimes you don't have the table. Okay? Sometimes you don't have the table and you just have bits of information like right-handed and male or probability of male. And you've got to use your brain and say, okay, well, I have these bits of information and I can put it into this form and get the answer that I'm looking for. Okay? Yeah, you're right. You know, when you have the table, sure, it's easy to say there's 430 males, and out of those, 385 of them are right-handed. So my answer is 385 out of 430. Okay? But it's not always that simple. And so this equation, this will always work, whether you have a table or not. As long as you have these bits of information, you can get your answer. Alright, so all of this, again, you've got to be comfortable with your fractions and your decimals, and we can do this. Alright, and so if you need to highlight this in your notes, make sure you can distinguish between right-handed and male versus right-handed given male, because they sound similar, they look similar, but the answers are very different. This one's 385 out of 900, this one's 385 out of 430. Okay, very different. Alright, so make sure you can tell the difference between this one and this one, because they are different. Yes? How many of these rules? I don't number them because then it's like discouraging. So I don't know how many rules there are. Okay, we're gonna fill up our class time with these rules. the time on the clock right now? 8 o'clock?
3 to 8.
3 to 8? Okay, let's take a 10-minute break, and we'll finish the rest of chapter 5 afterwards.